Welcome back to the channel. So today's question is Kth ancestor. In this, we have to find the Kth ancestor of the given node. So for this example, the node is 4. We have to find its Kth ancestor, which is 2. So for level 1 is 2 and level 2 is 1. I mean to say that this is level 1, this is level 2, L1, L2. For node 4, its K2 is 1, so its answer is gonna be 1. So how we can think of solving this question? To achieve the kth level of any node, we have to track all of them in a memory. For 4, I have to track its level 1, then its level 2. Similarly, if its level 3 also exists, for that we have to store all of them inside a level. So we can use a table in which we have to build a table. In this, we have to put the kth level and their node with their values. So that's the way of approaching this question. So let me discuss this approach. For the given question, I have built a table. So this is our table. Here you can see that in this table, row represents the node and the column represent the level. So these are the nodes which are mentioned in the tree and these are their level. So let's fill it up. For level 1, for node 1, its above level is there is no level above the 1, so we can fill negative for it, -1. For -2 for level 2, because nothing is present above 1, so all of them become negative. And for 2, we can see its level 1 is 1, we insert 1 over here, and above it nothing is there. Same goes with 3, only level 1 is present, which is 1, and the rest are negative ones, because negative 1 shows that nothing is present over here. It's an AND. Yeah. For 4, level 1 is 3, level 1 is 2, sorry, and for level 2 it's 1, level 2 of 4 is 1, and the remaining are my -1. Goes same for the 5. Level 1 parent is 2 and level 2 parent is 1, and the rest are negative of 1. Yeah, that's the way of solving the question. This is the one way we can solve the question. Now let me try run in this. Let's say if the question states that the node is 5 and we have to find its K2 means second level parent, which is gonna be 1. So how we can gonna find it on the table? So we can see directly here. The node is 5. Let me change the pen. The node is 5 and its level 2 parent is 1, which we can directly access from the table. So like this we can find we can get the answer easily. So we got the answer 1 over here. But there is a problem with this approach. Let me tell you. As you know that the value of n nodes can be 10 to the power 5, and the query also can be 10 to the power 5. So the total time complexity will become 10 to the power 10, which is greater than 10 to the power 8. As you can see that this can also goes till the 10 to the power 5, and this can also goes till the 10 to the power 5. For this question, the value of k is 100, for which you can use this directly, but I am just going to tell you the optimized approach of solving this. For this question, we have to use the approach in which we can get the value under 10 to the power 8. So for that, we are using the binary shifting. Let me tell you how we can use binary shifting for this. So binary shifting is a technique used in algorithms, especially on trees, to answer ancestors related query efficiently. Before that, I want to tell you one thing. 10 to the power 5 can be represented in binary in this way, which is around 16 to 17 digits. So instead of querying 10 to the power 5 directly, we are hopping from 2 to the power 0 till 2 to the power 16. Let me write it clearly. 3 and likewise. So instead of going from 1 to 3, we can hop from 2 to the power exponentially. We are hoping to gain the answer. Let me clarify you with an example. Now let's discuss how binary lifting is optimal. So suppose we have given the question, we have given a node X and we have to find its 100th parent ancestor. You can say without binary lifting, we have to go and manually fill the values of 100th parent. We will just start from here. If some value came over here, just like that, we just fill the entire table and we will get the value at the end. We will return this. That's a very high approach of solving this question, but whereas in the with binary lifting, we can just within the 17 iteration we will get the value of the 100 ancestor. How? So the binary representation of 100 is 11001000. Let me write it clearly for you. So in this tree, this is a tree. I didn't make a arrow, just understand this is a tree. So without binary lifting, we will just start from this node and we will directly access this 100th level node, which is a very memory taking approach, which is gonna take a very large amount of memory in creation, and which is not a very optimal approach of solving this question. So how this binary string gonna help us solving this question? So in the binary lifting, for all the set bit, we are gonna perform the operation. What is this operation? So let's say we start from this on bit. So from X, we will just access its fourth parent. From the fourth parent, we will just hop to not X 32th parent. We will just hop from this Y till its 32th parent, and from this Z we will just hop back to the 64th parent of this. So within the three operation we have accessed the 100 parent. So it is an optimal approach. For the K, it take log K time for solving this. Yeah, that's the way of solving this. If you want a detailed approach how to solve this, you can check out GFG blog for this, which is very pretty helpful to understand how this exactly in depth work. I just give you a approach of solving this, how I think about solving this question. So we are gonna try run with this tree for the binary lifting. So we have created a DB table, which we are I'm going to tell. So we have created a DB table. Its name is Ancestor. So for that, there is a thing we have to classify all the zeroth level parent. Zeroth level means 2 to the power 0, which is 1. So we will fill this level of parents initially manually by our own. The rest of the work done is by a loop, which we are going to run. This is the formula of solving this. I will let you understand how this works. Okay, now let's fill it manually. So once level 1 parent is -1, 2's level 1 parent is 1, which you can see in this example. Yeah, for 3 is 1, for 4 is 2, for 5 its parent at level 1 is 2. Now filling the level 1 parent of 0 at level 2, level 2 parent of 1, which we are gonna fill with this formula. How this formula gonna work, let me tell you. Let's say for node 2, I have to find its level 2 parent, which is -1. So how this formula is gonna help us find this? Let's see the inner ancestor table, which says that ancestor of I is the node is 2, of J is level, J level decrease by 1 always. So which is gonna say X is 2, so it's gonna be 1. So ancestor of 2 of 1 is, you can see here, ancestor of 2 of 1 is 2 of 1 is 1. So we're gonna fill it with 1. So it become 1. Now we will put in this red outer block, which is ancestor of 1 of 1, which is gonna tell us the level 2 of node 2. It says that 1 of 1 is minus of 1, which you can see that it's give us the final answer of minus 1. So we got the value from 2. Its level 2 is negative of 1, which you can clearly see. So by this formula we can access this easily. Yeah, that's the way of understanding this equation. Now let me fill all the values for you. So I fill the table manually for you. Let me tell you how this works. For level 2, this means for this, in this block level, this level says 2 power 2 is gonna give us 2. So this means this is a level 2. For 4, level 2 is 4th, level 2 is 1, which is 1. So by putting this in this equation, we will get the value of 4 at level 2 is, just put it over here, ancestor of I is 4, 4th level is 2, 2 minus 1 is 1, and over I is level is 2, 2 minus 1 is 1. So when we fill, when we will get the answer, ancestor of 4 of 4 row 4 and column 1, which is this, which is 2. You can see that 4 at level 1, its ancestor is 2. So we will get the answer 2. How we get the 2 from here? Because we manually fill the first level by our own. That's the way, and we will put in the equation, which is the recursive equation, getting us all the ancestor in an optimal way. So of ancestor of 2 at level 1, so ancestor of 2 at level 1 is 1. So we got the answer 1 over here. For 4, so ancestor of 4 at level 2 is become 1, which I have tell you with an example, which means for 4 level 2 is 1, which you can see that, which we got with the help of an example. So one thing at the end I want to tell you that we do not access the level 4 of we do not access node 4 level 2 directly. I mean to say that from 4 I do not jump directly to this level. For that I have moved from level 4 node 4 to level 1, means I move from level 4th node to its level 1, which is 2. So from this ancestor 4 of 1 I got the node 2. Now this is the node 2, and from node 2 level 1, from this I reach over the above one, which is node 2 we got from the ancestor 4 of 1. So that's how I hop from this level to this level. So in the figure you can see that there are two approaches, which one is 4 to 1 directly and the another one is indirect approach, move from 4 to 2 then 2 to 1, which is the binary hopping. The white arrow shows the binary hopping, the red one shows the non-binary hopping, which is a cost expensive approach or operation you can say, whereas the non-binary binary hopping is a cheap operation. So we are gonna use the non-binary approach that I told you entire video. Now let's code up the Kth Ancestor question. So I will make an integer int maxn, which is gonna having the value 17. As I told you, the 10 to the power 5 I let's write it side by side. 10 to the power 5 is equals to the 17 binary digits, binary string length, I can say that. For that I am using the max 17. Now let me make a function root. This is gonna give us the number of nodes in a tree. So this is our function which just gives us the number of counts of nodes present in the root. This is a pretty basic so code for writing this equation. I hope you understand it. So here I have built two vectors. One is a 3D vector which is ancestor. So as I told you earlier, in the binary lifting we have created an ancestor table which has all the values of previous parent in a binary way, in a hopping way, I can say that. And what is the use of parent vector, 1D parent vector? The use of 1D parent vector is to track of all the 1th level parent of all the nodes that we are gonna access with the help of a BFS function. That I will let you understand while doing a BFS. That is very easy for you to understand. So this is a DFS function that I have built to have all the level 1 parent of all the nodes. Let me tell you with an example with a dry run so you can easily understand it. So when I move in a DFS, so the parent of 1 is initially there is no parent of 1, so we'll mark it -1, which is root over here. So root have no parents. Now when we move downward in the BFS, so 2 has a parent 1, we marked 1 over here. Now when we move downward for 2, 3 and 4, we see that 3 and 4 has a parent which is 2. Now we go from right side of the tree, which is for 7 it's 1. Now for 5 and 6 it is 7. Yeah, that's a basic DFS approach in a tree. You should know it before doing this. For that you can check out videos on how we can traverse on the tree. Yeah, that's the way we have defined the parent. Now coming back to the question. Now I will fill all the 0th level or 2 power 0 means 1th level parent in the ancestor table. So this function fills all the nodes at level 0. Level 0 means 2 power 0, which is 1. So means level 1 of the ancestor table. Now I filled all the front line manually. Now the function will do the function I shared with you earlier will do this work by its own. So this function will fill all the values in the ancestor table. Yeah, that's I have already discussed in the video. Now I will move to the query part. So this part is where I have used the binary string conversion. Suppose I have already discussed, I have given 100. I have to find the 100 ancestor, which I can represent like this in binary. So I will compare this 100 with I. For all its set bit, I will just move to its ancestor level and I will access that node. And this from that node I will just move till the other ancestor which is set bit on in the binary string, then I will hop to that level and just get that node. That's how I'm gonna iterate over here. For this, let's say I start from 4. Ancestor node is initially x as x of 4th level. From that, if I get some value y, then I move till 32th level, then 32th level to the 64th level of ancestor to ancestor that I have shown you earlier in this question, in this explanation part. Yeah, that's the way of solving this question. Now let me discuss time and space complexity. Let us discuss both the time and space complexity without binary lifting and with binary lifting. So in this, I have to create a table, ancestor table with the n cross n values. N means so n can go from 10 to the power 5. So it is gonna give us n cross n, big of n square time complexity. The space complexity goes also the same because we are creating the ancestor table of n square size. In this, we are iterating till the log n, and we are creating a n sequence. So it is a n log n time complexity. Yeah, and space complexity is same, which is also a log n space time complexity. So this is an optimal approach. For this question, this also works, but if you understand this, you can solve all the competitive questions related to binary lifting. So I explained this with the help of a binary lifting. I hope you like the video. Like, share and subscribe, and the code is in the GitHub. You can check it out there. Thank you for watching.